the idea of Lie algebras, you have played around with it enough in your assignments. I guess you have done all that. So what I am going to do today is to actually discuss the Lorentz and the Poincare Lie algebras. Okay. Some aspects which are actually relevant to field theory, both classical and quantum. So the first thing is one thing we already know is that the Lorentz group is a special orthogonal group. So when by this I mean the continuous part, so we are looking at the special orthogonal group. There is a Lie group, and obviously there will be a Lie algebra which is SO1, 3, but the key point is, as Lie algebras, these are the same as SO4, and let me show you how this works. For that, it is enough for me to take SO. So a simpler example is to see how you would go from say SO2 to SO11. Okay. So by this equivalence, you remember when we discussed Lie algebras, it is a vector space. We could think of it as over complex or reals. Okay. So roughly what you will do is we start off with something which is in reals, and we go to the complex domain, and then we sort of choose a different section kind of thing. Okay. So let us understand how that happens. So let us look at SO2. So we know that any SO2, capital SO2 matrix can be written as cosine theta, sin theta, where theta is some angle okay, and we know that this is equal to e power theta times t, where t would be a 2 by 2 antisymmetric matrix. So this we know. So now the question is so the point I am going to make is that we can recover the boost matrix by taking theta and making theta to be pure imaginary. Okay. So let us look at so the step what we do is we take theta and we write it equal to I times some phi. Okay. So obviously I am so you can see that what I am doing here, theta here was real, I am complexifying it and then choosing something else, which is this. Okay. So now let us look at something like this. What is e power I phi of t? We can go back and look at it in this form, and can write it as cos I phi, sin I phi, minus sin I phi, and cosine I phi. Okay. Again, by going through the complex domain, we know that we can go from cosine the trigonometric functions to the hyperbolic functions, and in the complex domain they are the same. So for instance, we can look at cosine phi. So cosine theta is defined to be e power I theta plus e power minus I theta over 2. So if you just go ahead and put theta equal to I phi, we end up getting cosine. So what we see is that cosine theta cosine of I phi is equal to cos hyperbolic of phi. And similarly we will see you can show that sine of I phi is I sine hyperbolic of phi. Okay. So now we can see that we can rewrite this thing in terms of hyperbolic functions. You can see that the boost, remember the boost matrix was looked similar to this, except it was something cos hyperbolic of phi, sin hyperbolic of phi, and this thing. So this almost looks like that, except for this annoying factor of i's which hang around. So let me ask you, how do I get rid of this? Is there a way of getting rid of this i's? Actually not unitary, but a similarity transformation or a change of basis. So it is useful to go back to the original definition, and so you would have written something like this. For the norm would be, for a Euclidean thing, would have been v1 square, let me put it below, v1 square plus v2 square equal to 1, equal to is is invariant, not equal to 1 is the invariant. Okay. But for this thing we need to put a minus sign out here, either here or here, depending on this thing. So that can be achieved by taking one or either v. So if you suppose I want a minus sign here, I can take v2 to I v2, okay, and that will be realized on this as a similarity transformation. So I will just write here that this is equal to cos phi sin hyperbolic phi minus sin hyperbolic phi, no minus, the minus goes off, plus cos hyperbolic phi with some similarity transformation. Okay. So now you can see that similarity transformations are just a change of basis, that is not a big deal. Okay. But what I am able to show for you is that these two Lie algebras are really the same, but as complex Lie algebras. Okay. So when you go to these things, obviously these two are not quite the same. If you now insist that I keep phi real, then this is not the same as this, because that would be like a looking at it as a real Lie algebra. Okay. So but what we will do is I will always be thinking of going to the complex domain and coming back and forth. I will not specify that, and all the nice classification of Lie algebras is there only for the complex Lie algebras. For the real ones it is much more complicated, not that it is not there. Okay. So this is the way it is going to go, and you can see that the same thing will hold for this. Okay. Even the change of basis will be obvious, because you will have to put some i's in various places, but that is all there would be. And so you can see that this kind of is a nice thing as complex Lie algebras, they are the same. Okay. So now the question is, in your assignment you have shown, in one of your assignments you have shown SO4 is 2 copies of SU2. Yes, there seems to be a question there.
Here we proved that the groups are the same, right?
No, the groups are not the same. One is this group is U1, so theta here takes values from 0 to 2 pi, it lives on a circle, while phi lives on a line, there is no periodicity condition, they are not the same group, the groups are not the same. That is why I am very careful. I mean, you can see I have done this, I am not saying, I mean obviously something which is compact like a circle cannot become non-compact, I mean, so they are different. That is what makes boosts different from this thing. So at the group level they are not the same. Okay, and they are not the same as even real Lie algebras. In some sense, you can't put an I if you are in the real domain. Okay, so this is just this notation is carried over from the direct sum. These are also vector spaces. So it is like direct sum of vector spaces, and we also know that SO3 and SU2 are the same. Again, these two are equivalent as Lie algebras. So let us use this symbol. Okay. So intuitively you would think, maybe one, given SO4, I can look at an SO3 subgroup of that thing. You would think that would be one of these two SU2s, and then there is something complicated coming out, and that you might have seen that is not the case. What really happens, so the thing is, so the generators here there are 6 of these generators, because it is 4 into 3 by 2, which is equal to 6, and it is useful to write these generators as m mu nu, and it is antisymmetric under mu and nu. Okay. And so now I am what I have in mind is really the Lorentz algebra, but let us write out so these are the generators and there are 6 of them, it is antisymmetric. So, this equal, the notation is like this. Okay. So now the question here is what are these two SU2s, and you would have seen that first thing is to restrict mu and nu to take values only in the 1, 2 and 3. Okay. So that would be, so the notation we will use for that is ij. So let us do this m ij, it is again antisymmetric, but I can define something which I will call ji, which is half okay. So this will be your usual angular momentum in in non-relativistic quantum mechanics, whatever this, what you would have written. Okay. But we know that we get these boost guys when one of them is 0, and let us just call them ki. Okay. And so now the question is, so the thing is you can work out how these things transform. So one thing we already know is that ji, so in this fashion writing things out, ji jj is equal to I times epsilon ijk jk. This is just a normal thing which we know. Okay. Now comes the interesting part, what about j with k, and even this you can sort of interpret in the following sense up to a sign, I mean, yeah, okay, not even a sign. So we can think of this j as a generator of rotations, and this just tells you that this j is a vector, this index is a vector of SO3. Okay. So that more or less tells you how ki should transform. Okay. Okay. Now comes the last bit, which is kk. Okay. Now, so first thing it shows is that these 3 generators do not commute with j. So these two imply that you have 2 bunches of generators which commute with each other, they do not even talk to each other in some sense. So obviously this cannot be the one, and if you work this out, I am not going to use equal to because I am unsure about the sign. Okay. But what is more important is that this becomes I times epsilon I j k L k j k. Okay. So what you can see is that there are 6 generators, which is just a rewrite of the SO4 Lie algebra, but written in this form, and we get these things. And now the nice thing is that you can define Ni plus or minus to be Ji plus or minus I Ki. If you take these linear combinations, what you find is that they decouple. Okay. So roughly speaking, what we will see is that Ni plus Ni j plus similarly for minus, there is another SU2 Lie algebra. Okay. And the fact that they decouple implies, what does that imply for Ni plus and Ni minus? The fact that I can write it this way, they commute. Okay. Suppose just for a moment ki kj gave you kk, it still you would not say that it gave 2 SU2s because j and k do not commute. Of course, I do not think if I put this equal to k it will satisfy Jacobian identity, I am just saying suppose it had such structure of constants, then it won't be. So you need the, so what we have is two separate SU2s. So now if you are interested in representations of the Lorentz group, what you end up getting is two SU2s, and we know all about SU2s. Okay, so there will be, so irreps of SU2 are nothing but classified by spin, by some number j, which can take 0 for singlet, half for spin 1, 1, 3 by 2, so on and so forth. This one. Thank you. Anything else missing? Okay, good. So now because there are two SU2s, for each SU2 I will have a j. So now, but here we already know for SO4 through tensor method we know how to construct irreps of SO4, but what I am trying to do now is asking, trying to rewrite those guys in terms of these two SU2 labels, and we have to work back and forth. It gives you two distinct ways of writing the same thing, and this is very interesting and kind of tells you that maybe SU2 is the only group we really need to know very well, which is kind of true. Actually SU2 and the Heisenberg-Weil algebra, so these are the two things which I think one needs to know very well. Okay, so what we will do is irreps, so we have a new this thing, irreps of SO4 can be labeled by two numbers, by j plus and j minus. Okay, so it can, so these are like commuting labels, so you can give them this. Okay, so now for instance, so let us start working through these examples. The first one is, so I will just write numbers 0 0, what would this be? Scalar. Okay, so it is just a scalar one dimensional representation, so this is a trivial representation. Okay, so now comes the, so let us do something else. We can take a half and a 0. What would be the dimension of this representation? Spin half would imply how many? 2. 0 will imply 1, so 2 into 1 labels it will have, so this is a 2-dimensional representation. Have we seen a 2-dimensional representation of SO4? What was the smallest defining representation which we used? How did we define SO4 first? As what kind of matrices? How did we define SO4? Maybe in the second or third lecture. How did we define SO4? SON, say, how did we define that? The group SON, how? N direct, so it was a n dimensional matrix, so it is a n dimensional representation. Okay, so n equal to 4, so we wrote a 4-dimensional representation, but this way of thinking about it is giving, telling you that there is a 2-dimensional representation. Little strange, right? We haven't seen that. Okay, so this is a puzzle, we don't know what this is, but we could also had 0.5. This is also 2-dimensional, but it is a different 2. This is also 2-dimensional. So let us try something else. So what we are looking, let us try to find the 4-dimensional representation. Okay, so how would you, so the interesting thing here is that suppose we did consider this guy. This would be a half and a half. Half is 2-dimensional, this is also 2-dimensional, so it will have two kind of labels. This is 4-dimensional. Hopefully this is the vector of SO4. Okay, and there is a puzzle out here. Does anybody know what these two dimensional representations are? Huh? Okay, so this is called the spinor representation, and this is what fermions carry. Okay, so let me remind you, it is there even in non-relativistic quantum mechanics. We know that SO3. Okay, what is the smallest representation? Non-trivial representation. It's 3-dimensional. Okay, but we know that if you think of, so let me write the group, but we know that this comes from the Lie group SO3, but the Lie group Lie algebra SO3, but the Lie algebra of SO3 is the same as SU2, and SU2 has spin half representation, has 2-dimensional representations. Okay, so in some sense what you are doing is going to a bigger group. So the SO3 is not equal to the group SU2 again. Okay, from here we can go to SU2. Okay, so there is a sense in which SU2 is a covering group or whatever of SO3. So every element of SO3 here will have double this. So there will be a double valuation if you look at it from the SU2 viewpoint. Okay, and this is related to the fact that fermions, when you go around by 2 pi, actually pick up a sign. Okay, so you already have it even in non-relativistic setting, where when the minute you start talking about spin half representation, you actually are talking about going to the group SU2 instead of SO3. Okay, so that's exactly what is happening out here. And one more thing we can see here is that if you go back and look at this thing, what is Ji up to factors? It is just Ni plus Ni minus. I don't know if there was a root 2 needed inside this, but okay, so that's why I am using this. So what you can see is that our normal generator of rotations is actually this thing, it's addition of angular momenta, and we come back to this guy and ask what is the spin of this thing in terms of normal rotation. It's half plus the tensor 0, but this is just a half, this is also a half. So these are objects which we would have called fermions even in the relativistic non-relativistic setting. We would not distinguish between half 0 and 0 half, but that is there in the relativistic setting. Is that clear? So this is there, this is exactly like this thing, but it is at a different level for SO4. Okay, so SO4 also has these kind of representations. Okay, so these are actually representations of what is called the spin 4 group, but let us not get into those details. We are looking at only at the level of Lie algebra, so that I can avoid these complications. Okay, at the level of Lie algebra I have all these things. So these are fermions, fermionic or spinor. Okay, so these are called left and right movers. Okay, so we will call them, these are called Weil spinors. So one of them will be what is called plus chirality, another is called minus chirality. But you would have seen in your, when you did your relativistic quantum mechanics in Dirac equation, you had something called a Dirac spinor. How many components did it have? Huh? How many did it have? 4. Okay, so a Dirac spinor is actually a reducible under SO4. It is the sum of these two guys. So now we start getting nice things. So first thing we see is that Dirac spinor, which we know has 4 components, is in this thing. I am not proving these things, but at least I am trying to give you a flavor of where it comes from. And what conventionally what people do is to use an index alpha, which runs from 1 and 2 for this guy, and differentiate it from the other guy by putting a dot. Okay, so these are just 2-dimensional indices. So now let us look at this, something which has a half of this index, and this thing will have an index which is alpha alpha dot. Okay, so let us look at this guy. So half of guy, now that I have introduced notation, will have alpha alpha dot, and I am claiming this a vector. So you need something which will interpolate between alpha alpha dot indices and the vector indices, and that is done by, in the following sense, you just take sigma m alpha alpha dot, which I define to be for m equal to 0, I call it identity, I think, and it is just the identity matrix for m equal to 0, and the Pauli matrix is sigma I sigma mu, right. This is my okay. So, this is a very interesting. So, the most natural should I put with an upper mu? Okay, it does not matter. Okay, leave this way. So, I can think of constructing a matrix valued object. So, what this tells you is that if you give me a vector v mu, in this case a covariant vector, so that I can contract with that. This is what I mean by that. So, it lets you go from the normal SO4 vector index, which is 4 indices, to these alpha alpha dot index. Okay. But it is also interesting if you think of this as a matrix. Okay. So, then what happens is that this becomes a matrix valued, it becomes a 2 by 2 matrix, and you know that matrices do not commute. So, this is related to something called quaternionic things. Okay. So, but from our viewpoint it is just something which translates. So, this is called the bi-spinor notation, because it has 2 spinor indices, bi-spinor notation for a vector. Okay. I will do one more example and I will stop for this part, and to ask where does, suppose I have an antisymmetric thing like f mu nu, where does that sit? Okay. So, now because we are in 4 dimensions, we can break up, you can define f mu nu, you can take you can define its dual f tilde mu nu by epsilon mu nu rho sigma f rho sigma. Okay. And if you remember, this was the one where the electric and magnetic fields get exchanged from here to here, that is all. But now because this is an operation, if you do it 2 times, tilde tilde will come back to itself, I can actually form combinations f mu nu plus or minus f tilde mu nu. Okay. So, these will give you objects which are self dual. If you take the plus guy under this operation, it will come back to itself, the minus guy will go to minus itself. There might be an I here, it depends on the convention. So, I will not get into that detail, but what I am trying to tell you is that this breaks up actually into 2 parts, which is the self dual and the anti self dual part. This is something you can do only in 4 dimensions, because you can see I am using something very special to 4 dimensions, I am using the 4 dimensional Levi-Civita tensor. Okay. Because of that, what happens is that these are actually irreducible, each of these, the plus guy and the minus guy. Now, f mu nu had how many components? 6 components. So, each of these will have 3 components, and so what that translates into so spin 1 representation of this thing is 3 dimensional. So, this is one 3 dimensional and the other one is this thing. So, one of them will give the self dual part, the other will give the anti self dual part. Which one? Yeah, there might be some divide by root 2 or something like that. Yeah, yeah, there will be, yeah, obviously, yeah, even here probably I should put a half here and things like that, but I am just showing you schematically. This is not details can be worked out. I mean, you push me to a corner, I will work it out, but I think you should work it out. Apply 2 times and see what you get. What?
Minus half.
Where? I should put a minus here.
Okay,
No, it does not matter. It is really then, I mean, it is a question of what you will call self dual, what you will call anti self dual, they will get exchanged. That is not so important. Okay. Okay. So, what is important is this point I want you to remember, that a second rank antisymmetric tensor actually comes in this form. But again, this is also, we can ask how would we have seen this. Here is an example. We already saw a second rank antisymmetric tensor that under that broke up into 2 vectors j and a k. okay. And what is the so 1 plus 0 is a 1. So, this is like a 3 dimensional vector 1 plus 0 1 times sorry tensor, this is trivial in this. So, this is also 2 vectors, again we see this sort of a thing. And what we have done here also, that plus minus ik is similar to exactly this, because if you recall there is an epsilon coming here. So, it is really the same story, that we are going to n plus and n minus. In terms of representation theory, this is exactly that. So, again I mentioned there was some root 2 here, okay. So, might be there, but again that's all details for you to fix, not for me, okay. I just tell you what it looks like. I can fix it, but it is not relevant, okay. So, now let us so this is all I wanted to say about the Poincare group. What we not about the Poincare, about the Lorentz group, we have seen that all Irreps can be written in this form, okay. So, let us now look at the Poincare. So, it is a 10 dimensional thing. We have to add to mu nu, we need to add the translations. So, okay. So, I thought let me at least write something correct. Okay. So, this is a vector. So, this is a generator of Lorentz transformations, and we know that P transforms like a vector. So, it is similar to that, it will have 2 terms, but that is about it. P mu, okay. And using the same philosophy, I can actually write now m mu nu m rho sigma. I can write this thing. I just forget about the sigma for a moment, and then if you look at rho, that is a vector index, okay. So, we can see that. So, I just close that, and if you write that thing, you will get I will write only one term, and then the rest you can fill. So, for instance, I look at rho here, and sigma comes for the right. So, it just becomes I eta mu rho m nu sigma, okay, plus 3 terms now, okay. All the terms can be understood by saying you antisymmetrize with respect to mu nu, also with respect to rho sigma, or you just say that this rho gave me 2 terms, that is one vector index, then close this and then say that the sigma gave me 2 terms, and you write the other terms, okay. So, this is also, so there is meaning in all these things. So, you do not never need to really memorize a lot, just the structure actually fits, okay. So, the idea here is now what we are going to ask ourselves is, how do we can we write how do we classify reducible representations of this group, of this Lie algebra actually. So, but we got lucky in the case of SO4, it got mapped into something we know, which is these two. SU2 is only one thing which we know very well, and which I have taken for granted in this course. So, the question is, how would we go about doing this, okay. So, before that, so let us go back to SU2 and ask, so we I made the statement for SU2 that irreps are labeled by spin, okay. So, now the thing is that so in other words, if you take a spin j multiplet m, it is actually it has a whole bunch of guys m running from minus j to plus j in units of steps of 1, okay. So, now the thing is, can we write some operator which will pick out, will give us j for irrespective of, it will be whether which element we pick, and there is something, and that is the Casimir, quadratic Casimir. So, let us say the T A's are the generators, or J A generate SU2, then it is easy to show that JA commutes with this thing. Okay. So, in other words, because we know that these J's can raise lower can go from one multiplier to another. So, if you want something which is going to be independent of the M label, it better be something which commutes with all the generators of the group. They are called Casimirs. Okay. Such an example. So, anything. So, this is some functions of TAs which commutes with all the for all B belonging to the Lie algebra. Okay. Then we say that F is a Casimir. Okay. So, for SU2 we were done with J square, there is only one such label. What happens for SU3? For SU3 also you will find there is exactly this way, except the A will run over 8 of them, you sum over all of them with the natural metric, okay, and then you get again you get one such label, but SU3 actually has another one which is a cubic thing. So, you go ahead and define something called D A B C J A. So, let us write, okay, let us use T A T B T C, okay, where D A B C is something which you have to define, or you can equally work out what D A B should be. The horrible way to do it is to actually work this out with the requirement that this will commute with all of them. Okay. It turns out that for all the Lie algebras, if the rank is R, it will have R such Casimirs, independent Casimirs. Okay. So, for instance, so this will give you a cubic Casimir for this thing, and that implies that irreps of SU3 are labeled by two numbers, like 1 for SU2. Is that clear? So, what we have to do here is to ask, can we construct guys with commute with everything? Okay, and we will use this as a way of understanding that. So, the first point is to so commuting with mu nu implies that it has to be a Lorentz scalar. Okay. So, is there a natural Lorentz scalar we can construct? That is another way of saying, which will also commute with P, which is the only other generator. Now, the question 2 is, can you give me a Lorentz scalar with these guys? Obvious Lorentz scalar, P square, P mu, P mu. Okay. So, we can view mu nu, I told you is the generator of rotations. So, without calculations, this is a Lorentz scalar, we know it, or you sit down, you can do the calculation, you will get it. Starting from this guy, you can show that commutes. So, this is, so clearly the Casimir 1 is P mu, P nu. Okay. Now, it turns out that this has one more Casimir, so I have to construct it for you. Okay. It has a second Casimir. So, for that I will define something called W mu, which is the following: half okay. So, what is this? This is a vector, co-vector to be precise, but okay, I can raise lower and do stuff. Okay. So, this has a name, it's called the Pauli-Lubansky vector. Okay. Now, without calculation I can write for you its what do you call commutator with mu nu. Why is that? It is just a vector. So, Here it is exactly has to be the same as this, except wherever we see P here we should put W. Okay. So, just put the Pauli-Lebansky vector. Now, can we construct a new thing, new Casimir W square for the same reason as this thing, okay. But we need to check, So, first thing is we know this is trivially true, but we need to check one thing, that it commutes with the other generator which is P mu. This is only, I am not proving it, you can check this is exercise. Okay. So, now it is very clear that the second Casimir will be okay, and that is it, there are no more. So, now what this tells you is that any irrep of the Poincare group will have two labels. Okay. So, before we do that, so what we will do is that we will assume let us kind of look at objects which can be in representations of the Poincare group. So, if we take that to be a fundamental symmetry in nature, you would think that fundamental particles in nature should be in some irrep of this thing. Okay. So, we will just say make a claim or whatever. Particles, fundamental particles in nature arise as irreps. By the way, all this most of this discussion is due to Wigner, arise as irreps of the Poincare group. Okay. So, let us and these are labeled by eigenvalues of two things, two Casimirs P mu and okay. So, what would we call, what is the natural thing to call P mu the eigenvalue as the mass square, right. So, this we will call mass square, and the question is what is this. Okay. So, first step is to consider the case, there will be three cases to consider. Strictly greater than 0, this is a case of a massive particle. Okay. So, in this case we can always, there exists a frame where P mu rest, what is this frame called? The rest frame. So, let us ask what is W mu in such a frame. So, in other words what that tells you is that P 0 is the only remaining. Okay. So, now if you see this yeah. So, first thing you will notice is that W 0 is 0 in this frame, okay, but W I is up to some sign, it is half epsilon I j k m j k up to a sign. I need a little bit of a theorem or whatever, that the representation theory of realization of this Lie algebra on the space of functions or whatever is usually of this form. So, P mu is realized as minus I d mu, this is something we know. Okay. M mu nu is realized as I okay, but it could have some internal part which we have already seen in the case of in our field theory computations through another thing. There could be something else which we will write as S mu nu. Okay. So, this is how you would have a realization of this. So, if you assume we have something like this and you take this value of mu nu and actually wait, we can even do a little bit more. Let us look at m j k. So, yeah, so what would m j k be if you look at it? So, m j k will have two parts which we will write. One is the L j k plus L j k S j k, but what is L j k in a rest frame? It is 0. So, this actually can be rewritten as half epsilon I j k S k S j k. What m factor? Oh, there is a m. Thank you, because P 0 is m, that is important. Okay. So, what this tells you is that in the rest frame this is what happens, and you can see that so this is what you will usually call spin. Okay. So, W I square is just S square. So, W mu in this frame just becomes W I, which is nothing but m times the spin of the particle. In other words, if you give me any state, so any particle will have two numbers, one we will call m, the other we will call as this thing, and this is just W square equal to m square S into S plus 1, of course P square okay. So, implies that massive particles have two attributes, two natural numbers if you wish, two numbers associated with them. One is mass and spin. Is this clear? The second case is when P square is 0. This is what we will call massless particles. Okay. W mu is also 0 if both of them are 0. So, this is what we will call massless particle, but we will also put this condition in, and it is trivial to check from the definition that W mu P mu is 0 just from the antisymmetry of the P's. Okay. So, what you have is two 0 norm vectors in 4 dimensional space, and then because of that you can see that yeah, what is it, and they are orthogonal to each other. This can only happen if W mu and P mu are proportional to each other. The simplest way to do that is to go ahead and say take P mu to be in some frame where it is P P 0 0. Okay, and work out what you should get for W mu. It is not like W mu is some arbitrary vector, you should go back to the definitions, you will see that. So, these conditions imply that W mu is proportional to P mu. In fact, it will be not just that, you will find that W mu can be equal to lambda times P mu, okay, where lambda of course can be 0, can be plus or minus half, plus or minus 1, whatever. So, let us just focus on say this guy. Okay. So, this so you can a given particle can either take only one of these set of values, it can't be simultaneously half and 1, but the sign can be possible because you can switch things around, okay, up to a sign. So, this is called the helicity. Okay. So, a photon has m square equal to 0 and helicity plus minus 1. Okay. So, but if you take a spin 1 particle, while a massive spin 1 particle has 3 states, because it is in the spin 1 representation, while this has 2. Okay. So, this is something I have been telling you all along, that massless states are not represented by spin, but they actually carry something for helicity. It does not matter whether it is the analog of, see, the red herring is spin half, because a massive spin half particle has is 2 dimensional representation, while even the massless is 2 helicities. I would not use the word spin, actually I would use the word helicity, which is plus or minus half, but they are the same. I mean, so there is no now change in degrees of freedom, but you can see that if you go to higher things, higher spins, you see that that is not true. So, if you talk of graviton, which is spin 2, it is not spin 2, it is massless, it is supposed to be a massless particle with helicity 2, it is supposed to have 2 states from this just representation theory viewpoint. Okay. And all fundamental particles we know seem to fit into this. So, going back to our discussion of the Higgs mechanism. So, if a photon has to become massive, it has to get one more degree of freedom. That is exactly what is given by a scalar. Scalar is spin 0, which is 1 dimensional representation, it gives you exactly the one which makes up the difference. So, whenever helicity is not half, the key point is that you can never take the m going to 0 limit is not the same, they are different irreducible representations. So, it is not a simple limit, it is not just m being when some parameter m being set to 0, because m is not a parameter, it represents the it gives you it characterizes the irreducible representation of the Poincare group. Okay. So, there are other possibilities, for instance p mu equal to 0 and w mu not equal to 0, but then you will find that the spin can take here these were discrete values, here it can take, it will take a continuum, and we have not seen particles of this kind in our considerations. And there are more things you could, in terms of representation theory, you could say that I could have p square negative, okay, from again pure representation theory viewpoint, and that is again not something which we have observed in nature. Okay. So, particles seem to fit into only these 2 cases. I am done.